right? So it has a field E, B equal to is of length 2 bytes, C is of length 3 bytes, 2 bytes, and D is of length 64 an array of 64 characters, and the length field is within the map structure, right? Once it is done, what you are doing is that we are pushing these elements on the top of the stack, right? So in that way, instead of loading a single character, look at this one, we are storing only to 32-bit value on the top of the stack. Instead of doing that, what you are doing is that you are storing a multiple of that, right? So that is what you call it as a stack frames. And how to make use of the available registers, make use of the best use of the available register. Let us take for example, you have one register, let us take R0, right? R0, which is going to hold 32-bit data, right? But if you are able to store only 8-bit data in that, let us take I want to store only a single character into a register, then the remaining 24 bits are unused, right? So they're unused. So, okay, in that way we are simply wasting the very important resource of the system. So to avoid this one, what you are doing is that we are storing multiple values into a single register, right? Instead of holding only a single value into the storing a single value into the register, what you are doing is that you are storing multiple values into a single register. So in that way, you are just making use of multiple. Let us take, I have 14 useful registers or the general purpose register. And if you are able to store two values in one register, then it comes around, you can store 28 variables into registers, right? Instead of 14 variables, you can store 28 variables. That is the biggest advantage of, or even more than that also you can store it. If your data is able to, if your data is able to be put into 8-bit register, only 8-bit, then you can, in a single register, you can put such four variables. Like that, for 14 registers, you can put 56 register, sorry, 56 variables. This is the best advantage of the things. Look at this one. On a load and store architecture such as R, it is more efficient to access values held in register than values held in the memory, right? Uh, Storing in memory becomes it's costly in terms of the cycles, because you have to move the execution control. You have to give the address, memory address, and that memory address will be mapped and get the physical address. Once the physical address has been calculated, you have to fetch the value from the memory and you have to bring it to the registers. That will be costly in terms of the number of cycles, clock cycles that is being used by the things. So to avoid that one, there are several tricks you can use to put several 32 bit, sub 32 bit length for the, and that can reduce both size and increase the performance. What you can do is that you can store multiple values which is lesser than 32 bit in length, all right, into a single 32 bit register. So you can reduce the code as well as you can increase the performance as well. So let us look at one example. Best example here is that I have 32-bit register, right, which start from 0 index to 31 index, right? So what do you look at this one? Sample is equal to table of index, which is an array here. We are taking it, and the index values, and index equal to index plus increments, right? Index will be incremented by increment times, right? That's as simple as that. Now what you do is that you are storing increment in the first 16 bits of the 32-bit register, and index will be stored in the next or the high order 32 bits, or the high 16 bits of the high order 16 bits, right? So now look at this. So in a single register, I have stored two variables. In the first 60 bits, we have stored increment, and in the next half or the higher order 60 bits, we have stored index. In this way, we are just making use of the things. But one thing is that how to make use of this one, or how to have this one. One thing is that you first insert index into register, right? So index will be put into 16, first is 16 bit, lower order 16 bit. Then what you do is that you just left shift it by 16 bits. You left shift by 16 bit, then index will come here. So we have 16 bits, 0 16 bits here, unused 16 bits. What you do is that you just uh, put that increment value into the 16 bits. You just put the value of the increment into this 16 bits. In this way, you can store multiple variables into a single resistance, like 32-bit values into, sorry, so this is 16 bits and this is 16 bit. You are storing these values into a single register. Look at this one, end index equal to index which is left shifted by 16 bits plus the increment. What do you get it? Index plus index and the increment. Index is at the higher order 16 bits and increment is at lower order 16 bits. Now the question are how to get use of this one, how to take the values. Look at this one, LDRB, load the character from sample into sample. So table of index, what is that index? Index is here. Where is that index? It is 16 bit away from the beginning of the list, right? Beginning of the register. That's why what you have to do is that have index IND INC, we have it, and which is left shifted by 16 bits. It is pointing here, IND INC is pointing here, and this is going to be shifted by 16 bits. It is 16 bits you shift it, and you will get the beginning address of the index, and that will be considered. And how to get the increment value? How to get the increment? That is very important, right? So that is the add index plus index plus index, right? Index is here, so we are doing that. Is it right? And this is index. Here it is pointing here, and it is left shifted by 16 bits, right? So you will get index, and that is being added to the beginning of the address. That is in the increment plus the increment. Whatever the value will get it, it is going to be put into index itself. It is pointing here, and it will be stored into the into uh, the the address where it has been pointed by index. Like this, you can store multiple variables into a single register. In this way, you can have or you can utilize a single register to store multiple variables. So look at one more example of the things here. I have 32 bits, right? I have 32 bits, and the shift value will hold only 8 bits, right? Shift value will hold only shift 8 bits. So what you do is that we are storing another variable count into remaining 24 bits. Count value into remaining 24 bits. So what you do is that count shift is equal to count is left shifted by 8 bits, left shifted by 8 bits, right? And for that one you are adding shift. For that one you are adding shift, right? So like this, for the first in the first 8 bits you're storing shift, and in the next 24 bits we are storing count. So look at the example here. Register R0 is holding the address of the output array. Register 1 is holding the address of the input register, input array, and the count shift. So register 2 is holding. It is stored into. It is considered as a count shift, right? Right, count and the shift rightmost amount. That is in R2 we are storing both the values. That's the count and the shift. And R3 is having the value x, right? So what you do is that add count shift, right? 39, which is left shifted by 8. So now what is the value of count is 39. The value of count is 39, and that will be left shifted by 39, sorry, 8 bit, and whatever the value you get it, that will be stored back into and that will be stored back into count sheet, right? So then what you're doing is that you want to access the value of right in 4 bits values here. Subtract 1 1 from the value of the count, right? So to get that value of the count, what you do is that you have to left shift it by 8 bits. You have to left shift by 8 bits, and whatever the value you get, whatever the address you get it from, that address you just get the value and subtract it 1, and once the subtraction happens you store it back into count shift itself, right? So again what you're doing is that move x comma x, right? ESR count shift by shift times and so on. The whole idea is that this is very important because you're just making use of a single register. You're just making use of single register where you are storing both the values, that is a count and the shift. And what happens for each value, you are decrementing for each iteration, the value of count is decremented by 1, right? And after 39 iterations, right, 39 loops, it will be get terminated. It will get terminated because the count shift the count value is 39. For each iteration it is decremented by 1, right? It is decremented by 1, and after 39 iterations or the loops, so you are going to terminate the string, or you are going to end the things. So the whole idea is to uh, understand how to store multiple variables into a single register. In the previous example, both the values are stored into 16 bits. First 16 bit means the first 16 bit we are storing increment, in the second 16 bit we are storing it into storing the index value. But in this case we are storing uh, shift in first 8 bits, and the remaining in the remaining 24 bits we are storing count value, right? That is what uh, the advantage of storing multiple values into a single register. So what is the summary of the memory allocation? ARM has 14 available register for general purpose usage, that is R02, R02, R12, and R14, right? There are 14 registers. And the stack pointer R13 and the program counter R15 cannot be used for general purpose data. Operating system interrupts often assume that the user mode R15 points to a valid stack, so don't be tempted to reuse R13. R13 is meant for the stack pointer, and R15 is used as a program counter register. And if you need more than 14 local variables, swap the variables onto the out to the stack, working outwards from the innermost row, right? Or we have studied how to make best use of the available 14 registers. So what you do is that if you have more than 14 local variables, what you do is that you store it on the top of the stack, okay, and swap in between stack and the registers. Use register names rather than the physical register numbers when writing the assembly routines. This makes it easier to reallocate register and to maintain the code, right? As you, instead of the register names, work like use the register name instead of their register numbers, right? So you give an temporary register name so that you can while writing the program. To use the register pressure, you can sometimes store multiple values in the same register. That is exactly what you have done. You have stored multiple values into a single register. For example, you can store a loop counter and a shift in a one register. You can also store multiple pixels in one register. That is also possible, right? Instead of storing one value in one register, what you're doing is that you're storing multiple values into a single register. Okay, that is what the things. And the next topic is conditional execution. The processor can conditionally execute most ARM instructions. This conditional execution is based on one of the 15 conditional codes. Conditions in the sense that if it is lesser than, greater than, lesser than or equal to, greater than or equal to, right? So they are called as the conditional executions, right? If you don't specify a condition, the assembler defaults to the execute always condition. Execute always condition will be execute if you don't specify any condition. The other 14 conditions split into 7 pairs of complements, right? They are converted into 7 pair of complements. The condition depend on the 4 condition flags, code flags, that is NZCV stored in the CPSR register. So it all depends on the conditional codes, right? Conditional codes that is stored in the CPSR register. That is the conditional execution in the sense that based on certain conditions you are executing the codes. There are 15 conditional codes we have it, and using these 15 conditional codes you are if the certain condition is met, you are jumping or you are transferring the execution control. That is what the idea here. So by default, ARM instructions do not update NZCV flags in the ARM CPR, right? ARM instructions doesn't implement or doesn't update the values of these one, that is the NZCV flags in the ARM CPSR. Instead, you have to suffix with the S, right? To make this updation into the flags, what are you supposed to do? You have to use a suffix, or you have to append a suffix S to the instruction mnemonic. By combining conditional execution and the conditional setting of the flags, you can implement simple if statements without any need for branches. Using these one, you can implement this simple instructions without using any need for the branch instructions. What is that conditional execution in the sense? You are using these conditional codes 14, basically 14 condition codes plus one execute always condition. What you're doing is that you are executing certain conditions, right? And these conditions are based on the flags set in the CPSR register, right? So ARM CPSR register, for most instruction to update these flags, right, we are using or we are appending S suffix to the instruction manual. By combining conditional execution and conditional setting of the flags, you can implement simple if statements without any need for branches. Look at one example here. One example of the condition code. What you are doing is that if I is lesser than 10, if I is lesser than 10, what you are doing is that C is updated to I plus ASCII value of 0. Means that you are converting and lowercase letter to uppercase letter. That is what the syntax is going to do. If I is lesser than 10, what you are doing? Not this one. You are going to convert your you are going to convert your decimal number into ASCII values. So are the hexadecimal equivalents, right? If I is lesser than 10, what you are doing? C is equal to I plus that ASCII value of the 0. Else, what you're doing is that C is equal to I plus ASCII value of I. This is subtracted with 10. That will give the decimal equivalent of the hexadecimal number. So look at the other equivalent code for this one, CMP, that is compare I with 10. Compare I with 10. I is lesser than, I is greater than, or I equal to 0 or not. If add less than, lesser than, what is that? C comma I comma, it is added with the ASCII value of 0. If it is lower than, so you just do this one. Else, what is that? If it is higher than, what you are doing is that C comma I hash of a minus 10. This is exactly being converted here. If I is lesser than 10, I'm comparing the value of these two, right? If it is lesser than, what I am doing is that I am just C is get converted into I, which is added with the ASCII value of 0. Else, if it is higher, what I am doing is that I'm just converting C, sorry, I, which is added with the ASCII value of I subtracted with that. That value will get stored into C. So when the comparison happens here, the string, it is going to update the values into things. In this case, we have not updated or we have not suffixed with the S. Means that it is not going to update the value of the CPSR flags, right? So here is one more example of the conditional flags. If A, C is equal to A, or C is equal to E, C is equal to I, or C is equal to 0, or C is equal to A, means that if the character is a vowel, I am updating the value of the vowel, right? Vowel plus plus. If C is equal to A or E or I or O or U, you are incrementing and counter code as whole 2, or you are advancing it by 1. So look at this one, right? Temp TEQ, C is equal to A, or if it is equal to A, or if it is equal to I, if it is equal to O, or if it is equal to, if anything is true, and if it is equal, OL equal to OL plus 1. If anything is true, if any one of them are true, then and if they are equal, OL is equal to OL plus 1 it is. OL is updated to OL plus 1. That is what we have done in the increment operator, right? If any one of them is true, if any one of them is true, and 1 to OL. That is what the, so that is how we can make the write the simple assembly instruction equivalent to the C codes. So here is one more example how to write the, or how to convert and how to count the number of characters in the given input. If it is, if the C is greater than or equal to A, or lesser than or equal to a Z, or if the character is greater than or equal to small a, or and if it is lesser than or equal to Z, so it is a letter. That's why I'm updating it to letter plus plus. Is it right? That is, if the character lies in between A and Z, or if it lies between small a and capital Z, sorry, small a and small z, I'm updating the value of the letter. So what I'm doing is a temporary C is subtracted with A, right? Compare with Z minus A, right? What you have is that you're just comparing with the A, subtract. So what is that? Temporary subtract if higher than C and A and all things, right? It is uh, what I'm doing is that these you just to go through these instructions: subtract HI, compare HI and LD, add LS, right? So that will give, that is going to convert this instruction to, if any one of these is lesser than, if this is true, I'm just incrementing the value of the letter by one time, letter by one time. So next one, it is the looping constructs. Most routines critical to performance will contain a loop. You are having loops in your applications. More routines contains critical to performance will contain a loop, right? Any loop, any routine may contain the loops, and these loops will add to the performance of the entire program. All loops are fastest when they count down towards 0. That is, if you start uh, from 0, sorry, from n to 0, and the loops will be faster. Otherwise, if you count it from 0 to n, they becomes they, they they become slower one. That is what the things, right? The most routines critical to performance will contain loop, right? The routines usually contains loop, and these loops are faster when they count from n to 0. Look at this example here. Move I comma n is moved to I, right? Subtract 1 from I, right? And store it to become strong. If it is greater than, loop it back. That is, it starts from n to 1, or if it ends to 1. So that is, you are starting from n and you are going up to 0. Yeah, sorry, you are going up to 1. That is what the body of the loop instruction. And here is one more example which counts from n to 0, right? Initially we are uh, we're just subtracting it by 1, right? Subtracting it by 1. So what you do is that you're just subtracting 1 by 1 with I. So and the value will be stored back into I itself. If it is greater than or equal to 0, so loop it back. That is, it starts from n. It start from n. So initially n will be subtracted by 1. That is n minus 1, n minus 2 up to 0. So here what you has, it is 1, it is n minus 1 up to 1. Why it is? we are using the conditional code called as the BGT, that is a branch if greater than 2 or greater than 0, greater than 0. Here what you have, greater than or equal to, greater than or equal to loop, right? If it is 0 also, it is just counting it, right? Once it becomes -1, you will stop it. So, and here is one more example, right? So there is no compulsion that you have to decrement the value or increment the value by only a single value, right? So you can decrement it by any number of times. Look at this one, move I comma n. So I n value will be moved to I, and it is get subtracted with 3. That is, for each iteration the value of I will be decremented by 1. So it is get decremented by 1, right? And if it is greater than what I am doing, is just looping it. And the first iteration it is n, and the second iteration it is n minus 3. In the third iteration it is n minus 6, and so on, right? For each iteration, for each loop, we are decrementing it by 3 values. Is that right? So that is what the looping constructs. You have it. Looping construct. Most routines critical to performance will contain a loop. ARM loops are fastest when they count down towards the 0, right? When they count it from n to 0, so they are much faster. In this case as well, you are counting it from, what is that? Counting it from n to 0, or n to n to 0 or n to 1, or in this case uh, counted from n to 0 as well. That is what the looping construct is. Unrolled counted loops. Loop unrolling reduces the loop overhead by executing the loop body multiple times. What you are doing, you are just uh, executing the loop body multiple times. In that way, loop over unrolling will execute or reduces the loop overhead. There are problems to overcome. What if the loop count is not multiple of unroll amount? What if the loop count is smaller than unroll amount? So what it means is that I'll specify the number of times the loop should execute it. Let us take I'll specify the unrolling amount as 3 3 times, right? For each loop you have to execute 3 times, right? So if the number of if the loop count is not a multiple of the unroll amount, let us take if it unroll amount is 3, and the loop count is only 7, right? 7 is not a multiple of unroll amount. Then in that case, what is supposed to do it? What is supposed to do it? And what if the loop count is smaller than the unroll amount? Let us take unroll amount is 3 and the loop count is only 2, right? What in that situation, what is supposed to do? That is a problem that comes with the what you call it as unrolled counted loops. And we'll take the C library function memory set as a case study. This function sets n bytes of memory at address S to the uh, byte memory address to the byte C value. That is memory set, which is going to set the value, sets n bytes of memory at address S to the byte value C, right? So we are just assigning n bytes at the beginning address of S to a value called as a C. To be efficient for large n, we need to write multiple bytes at a time using str or stm instructions. Therefore, our first task is to align the RI pointer S. However, it is only worth us doing this if n is sufficiently large. Only thing is that you're supposed to initialize the value of n in such a way that it must be a multiple of some number, right? So that you can store multiple values into memory instructions, and where S is pointing to the beginning of the memory item. That is what the unrolled counted loops it is. Just remember that unrolled counted loops are nothing but loop unrolling reduces the, what you are doing is that you are executing uh, the loop body multiple times. That is called as the unrolled counted loops. Okay, and multiple nested loops. We can combine loop counts within a single register, placing the innermost loop at the highest point positions. Right. What you can do is that you can loop counts can be stored into a single register. Right. Placing the innermost loop count at the highest position or the highest bit position you can. So to understand it, we have an
నీలి నీలి ఆకాశం ఇద్దామనుకున్నా మబ్బులు నిన్నే
right here is a classical example of nested loop. I have three loops here. What it will do? What's it going to do? Can anyone tell me? Yes? Yes? Can you hear me? Can you hear me? Any one of you?
Yes, sir.
Seema? Seema R?
Yes, sir.
Seema R?
Yes, sir.
Okay, what it is doing? Yes? Hmm? Chandrakant? Chandrakant?
Yes, sir.
So what it is doing? This loop? Yes? Yeah?
All one is sir.
Pardon? ಏನ್ ಮಾಡ್ತಿರಿದು?
ಅದೇ ಕಾಲ್ ಬಂದಿತ್ತು ಸರ್ ಮಾತಾಡೋದು ಸರ್.
ಹೌದ್ರಿ ಕಾಲ್ ಬಂದಿತ್ತಾಯ್ತು. ವಾಟ್ ಇಟ್ ಈಸ್ ಡೂಯಿಂಗ್?
ಹೌದು ಸರ್.
ಹಾ ಏನ್ ಮಾಡುತ್ತೆ ಇದು? Can you see this one?
Yes, sir.
Are you able to
Yes,
see
sir.
this one? Chandrakant?
Yes, sir. Yes, sir.
Yeah, what? Just see this C code and tell me what it is doing.
Multiplication.
Yes? Chandrakant?
Yes, sir.
Matrix
ಏನ್
multiplication.
ಮಾಡುತ್ತೆ ಇದು? Others don't reply.
Not understood.
ಏನ್ ಮಾಡುತ್ತೆ ಇದು?
Multiplication.
Matrix multiplication.
Matrix multiplication.
Yes, sir.
Huh?
Multiplication.
Yes, sir.
Matrix multiplication, right?
Yes, sir. Yes.
Concentrate ಮಾಡ್ರಿ ಇಲ್ಲಿ. ಹಾ
What, sir? Yes, sir.
ಮೀಟ್ ಮಾಡ್ಕೊಂಡು ಕುಂದ್ರಬೇಡ್ರಿ ಎಲ್ಲ.
No, sir.
Right here we have a classic example of storing the thing or multiplying two matrices and storing the result into a resultant matrix, right? This is R is 40 and S is 40 and T is 40 as well. So what I am doing is that I am multiplying the two resistors, right? Sorry, two matrices, the elements of the matrices, and the same will be added to sum, right? Once that is done, sum will go to A, right? The each element of B is multiplied with C, each element of C, and the sum, we are calculating the sum. Once it is done, it will go to E, right? So here what I'm doing is that we're storing the values, these values into a single register, anyhow. You know that these matrix values are very small one, right? So they can be put into a 8-bit values, right? So what they are doing is that the innermost loop we have it, that is for loop, and which contains s and k, right? S, right, and k. What I'm
Yes.
doing is that it will be placed in the higher order 8 bits. It will be placed into higher order 8 bits, and the next one, it is t and g, that will be placed in the next higher, sorry, lower order 8 bits, and I and r, that will be stored in the lower order 8 bits. That will be stored in lower order 8 bits. So like this, a single value, or a sorry, single register can be used to hold multiple values of a loops, right? We have multiple loops here, one loop, two and three loops, and the value of all these loops will be stored into a single register, right? And each value will occupy 8 bits. 8 bits in the sense it is from 0 to 256. This is also 256, and this is also 256. That is, you can have, you can have a matrix of size 256 by 256. That is what, right? So this is how you can convert your code into registers, right? So just don't go deep into the things here. Just remember how we are going to store these values into registers. Look at this one. So initially we have something called as we are storing r minus 1 into first 8 bits, that we are doing it, right? And then what we are doing is that we are to store t minus 1, which is
Next.
left shifted by 8 bits, and for s minus 1 it will be shifted by 8 bits. It will be shifted by 8 bits. So
Bits.
you get the you are storing these three values into into a single register. To access that one, you are supposed to shift it by that minimum number of times. And here you can store the value of count here. Count is equal to, they're giving a name called as a count. So what they're doing is that if you want to get the value of some values, so you have to use that count, because that is the name I am giving to a register, 32-bit register. What you do is that you just use that register to access a particular value within the register. Look at this one, count, which is subtracted with 1, that is 16. What is that 16? Left shifted by 16. When you left shifted by 16, you get t, right? T, right? Sorry, k will get it. So that is what we are doing it, right? Similarly, we have something called as the count, which is left shifted by 16 bits, which is left shifted by 16 bit.